Hello, this is my new channel and this is videos number 3. I'm going to run a demonstration of particle swarm optimization, and now I will step through a series of introductory slides. Particle swarm optimization is a numerical optimization algorithm based upon a set of communicating particles. It's a heuristic algorithm, and the particles are connected together to form a circle. In each particle, a vector is stored that represents the solution. Particle structure. In each particle, there is the current solution, the previous best solution. Each particle has a node ID, and each particle links to an adjacent particle. A single particle also holds the global best solution. It's also, in the system, there's also a copy of the previous step vector, and this is a momentum term. There are two modes of operation, local and global modes. The local mode only uses the nearest neighbor, and the global mode uses the global best particle. PSO is an iterative algorithm. A PSO step takes the difference between two scalar vectors. The step is multiplied by a scaling factor A and a random number in the range 0 to 1. Step old takes the previous momentum term, step best the previous best stored solution, step local involves the nearest neighbor or the best nearest neighbor, and step global uses the global best solution. The final step that is made is actually the combination of three vectors: step old, step best, and step local in local mode. If you look in this here, this particular step is replaced by step global in the global mode. And what now happens, you have the old solution and you add the new step to it to get a new solution. The rate of convergence of this algorithm can be adjusted by changing the value of A. Let's just go back one step. And A is this value here, down here on the step vector. This is a fragment of the class file PSO run, showing that the population size is 30, the iteration count is 1000. There's a switch to switch off the print functions. ACLI is an alternative function that we can solve. At the moment it's currently set to solve the sine wave problem. There's a restart function which resets the current population to random values. If you put 4 in that location, you get 4 resets during a run. To ensure that you can observe the screen during a run, there's a small delay in 200 milliseconds, and the pop call is the actual number of variables in each row vector. Since we're looking at a 2D system, this value is only 2. Right, what we're looking at here is the class file PSO1. So in this particular version, I would arrange to adjust the A values between start and finish. So in other words, you have a large value at the beginning and a lower value at the end. S for start, F for finish. This is the previous best, local, and global. If we want to make these constant during the operation, you just make these two values the same. So here we've got the global is switched off because it's 2 zeros, and the local is active. And over down here, we look at if you look at these values, these are quite high. Here it's fixed, and it's fixed here and fixed here. And what happens is, if we run this, you find that the system doesn't converge very quickly, if at all. Right. So we're solving a sine wave function where the variable rate goes between 0 to 2. The solution point is 1 and 1. So we get the maximum, in other words, it's 1 over 2, 0.5 pi upon 2 radians, which obviously gives them a value of 1. And that's on the display surface, that is the center of the display. This was originally written in Ball and JBuilder, but it runs within Netbeans quite happily. Here's a screenshot. Again, we've got the class files, functions and variables, the code. This is Netbeans, and the PSO project is loaded. What I'll do is I'll do a clean build to show that it's built successfully, and I'll run the project down here because it takes a while. Now, pop size, that's the number of particles. Iter is the number of iterations, so it's only 200, it shouldn't take too long. And the delay is 200 milliseconds. So what we're looking at here, this is the ring of particles searching for a solution. The solution is in the center of the screen, and even though this seems to be taking quite a long time, it is actually doing an exhaustive search of the region to try and find a solution. I've found that this to be quite effective on various types of projects that we've applied this algorithm. What I'm going to do now is switch across to a different function and turn off the first set of options and look at this option. Sorry, put a 1 in there. And this here we've got quite large values for the variable a, and this causes the system to oscillate. So clearly, if you set the incorrect value for the a term, then you may not get a satisfactory solution. I'll stop this now. The next thing I'm going to do is turn that off, put a different value in. That will return the true if 1 equals 1, which is obviously true. So now what we've got is these values are too slow, or the convergence will be too slow because these are quite small values. I'll run this and you get in to see what I'm talking about. It is finding a solution, but it's not necessarily searching the domain particularly well. But nevertheless, it is converging. What I've found is that the best performance is gained when the particles jump around in the search space. So I'll stop that. Close this. Now the next thing I'm going to do is actually look at the global search. The previous three were all local because we've got zeros here and values here, whereas here we've got the global value set and this is 0. So off we go. You can see that quite a very fast performance, finds the solution very rapidly. The next thing I'm going to demonstrate is what happens if you put a very large population into, say we'll have 100 in the population, and we'll still, I'll go back to this model, the local model, switch this one off and see the performance. You can see that the set of particles is effectively searching the whole of the two-dimensional surface. This takes quite a long time to run because we've increased the number of particles, but it will generate a solution. I'll stop that now because it takes too long. Okay, that completes the this demonstration. I hope you found it interesting.